Today we're going to take a look at a different way of writing exponents. And that is called log. So this will be a review of last year. You started to take a look at logs. So log base b of c equals a if and only if b to the a equals c. So one thing to note, our bases are the same. And then a log solves for the exponent. So a couple things. Our base has to be greater than 0 and b can't be 1. So if you were asked to rewrite these as log equations, or as exponentials, our base is 3, so it'd be 3 to the power of 4 equals 81. Now this next one, our base is 16, so 16 to the 1/2 equals 4. And then rewrite as logs. So it's going to be log base 125 of 5 equals 1/3. Because again, a log, think about it like a log in a forest, it chops down that exponent. So this one, sometimes I write, so our exponent equals log base 10 of 1,000. Now if you need to evaluate the log, one thing you'll notice here is that there isn't a base. That is what is called the common log. So log base 10 of x equals log of x. So if you don't see a little base, you can assume there's a 10 right there. So we need to evaluate this. So what does this equal? We don't know. Well, if I was to write this as an exponent, 10 to some power equals 100. So that would be 2. So this one, again, we don't know what it equals. So this is 2 to something equals 1/32. Well, wonder what this could be. Well, I know that this is equal to 1/2 Well, since it's flipped down, it has to be -5, because a negative exponent would flip it. Now this one, let's see. 4 to the x equals 25. Well, there isn't any power here, so this would be one to type in on your calculator. And on your calculator key, you'll see it in blue right above the 10 to the x. So you do control 10 to the x. Now, since I don't have a calculator, I'll just have to do it on Desmos. So on Desmos functions, I can go down, and it is log right here. So log base 4 of 25. 2.32. And that makes sense. Well, 4 squared, if I did 4 to the squared, that's 16. 4 to the cubed would be too big. And so this one, log of 39. Again, on Desmos, it's under functions. Log. If I don't put it, it assumes it's base 10. Oh, maybe I do have to put a base. So log base 10, 1.59. I don't know if there's just a regular, if a common log is on here. Oh, yep, there is. So log of 39. You'll see we get the same thing, 1.59. So now we're going to take a look at some more things with, why do we have logs? Like, logs is a different scale. So for example, here is the average length of some videos in seconds. So if I was to graph these on what we're going to call a linear scale, let's see, this would be 0, 2,000, 4,000, 6,000, 8,000, and 10,000. So you'll notice we're going up very evenly. So Sully is at 505. So here's Sully. Bruce is at 830. Bean is at 1,000. And then Kelly is way up over here. So that's our linear scale. We're going to graph it on like a log scale. And we're going to start like log base 10. Okay, so if it's log base 10, this is going to represent like 10 to the 0 power, so that's 1. 10 to the first, so 10. 10 squared, 100. 10 cubed, 1,000. 10 to the fourth, 10,000, and then 10 to the 5th, 100,000. So if I was to go and I was to type in all of these, and I'm going to find the log of them. So I'm asking myself, so if I was to find log base 10 of 505, what does that equal? I'm saying 10 to what power gives me 505, right? So I can go back here, and let's see, I'm going to type in 505, so 2.73. So this is 2.73 in log land. In this one, again, I'm doing log base 10 of 830, so I'm asking myself 10 to what power gives me 830? So log of 830, so 2.91. So if I finish these, I would have 3.2 and let me log of 10160.4. So if I graphed these, we're graphing, to what power? So 2.73, well, here's 10 squared, 10 cubed, so 2.73 would be right here. 2.91, 3.2, and 4. So we can see they're not quite as spread out there. So this is our log base 10. We could also graph it with a log base 5 scale. So over here, so we're figuring log base 5 of whatever and seeing what that equals. And again, we're saying 5 to what power gives us the value of 505. So this one would be 5 to the 0, 5 to the 1st, 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th. So pause, and I want you to type all of these in with log base 5 and then the value. All right, so if you do that, we come up with, this one was 3.68, 4.2, 4.5, and 5.7. So if we graph those, 3.68 is right here, 4.2, 4.5, 5.7. And we can see, again, they're definitely not as spread out as the linear one and a little bit more evenly spread out. So log scales are used in all sorts of different things. Like the Richter scale uses a log scale because an earthquake of a 5 and a 6, it's not evenly spaced out. It's really a power of that. So like 10 to the 4th, 10 to the 5th, it is that strength there. So if we were to rewrite these as a log statement, this would be log base 16 of 8 equals 3/4. And this is our basis, so 32 to the 2/5 equals 4. And evaluate when this one is 5. So let's see, log base 25 of 5 equals something. So 25 to the something equals x equals 5. And again, so that's the square root, right? So our something would be 1/2. And this one, let's see, so log base 6 of 12, what does that equal? 6 to something equals 12. Well, this would be a calculator. So you could type that into your calculator because we couldn't figure that out.